Today we're going to study some of the basic applications of multiple integrals. First example is the area of a planar region. Let's say we on the two-dimensional space we have a bounded closed region like this. Let's call it D. And we say this region D has an area if this multiple integral exists. Okay, so this is the integral of a constant function that is, so to speak, f of xy is equal to 1. So this is a constant function. If we integrate this function over on this region, on this bounded closed region, and if it is it has a value, then we say this region D has an area, and we usually write this area as mu of D, like this. So this is the area of D. Let's see an example. So let's see, say we have a bounded closed region defined by this set xy x squared plus y squared less than or equal to a squared. And so this is a circle with radius a, suppose a is positive, and centered at the origin. So the area of this region can be calculated by this integral. Now to calculate this, we use the polar coordinates. So by using this, we have dx dy equals to, as we have calculated before, the Jacobian is r, and dr d theta. So this will be d, let's see, a and 2 pi and r d theta dr. So that is 2 pi r, and that is pi r squared and pi a squared. So that's the area of the circle. Okay, the next application is the volume of a solid figure. So that is in three-dimensional space. Let's see, we have x, y, z. So this is r cubed. We have some shape, it's a solid shape, which is three-dimensional. Something like this. So let's say this is a bounded closed region in three-dimensional space. Let's call it V. Then the volume of this solid is defined as this. So this is triple integral on this bounded closed region, and dx dy dz. So if this is finite, then we say this solid V has a volume. Okay. As an example, we would like to calculate the volume of a sphere let's call it B. It's a three-dimensional ball, which is defined as the triple of real numbers x, y, z, such that x squared plus y squared plus z squared is less than or equal to a squared. So this is the sphere with radius a centered at the origin. But before executing the triple integral of this region, it is convenient if we know the spherical coordinates. Okay, so let's define that. Just like the polar coordinates in two-dimensional space, we express every point in the three-dimensional space by the distance from the origin and some angles. But in this case, we have to use two different angles. So let's see, x, y, z. So let's say we have a point here, and we calculate the distance from the origin, and that is r. And then we project this point onto the xy plane. And the angle from the x-axis is phi. And the angle from the z-axis is called theta. So this triple of r, theta, and phi defines the spherical coordinate of three-dimensional point. So how do we transform xyz from r, theta, phi? Okay, that is actually defined as this. So z is easy. So if we project this point onto the z-axis, so it's something like this. So this length should be, since this is theta, it should be cosine theta times r. So z is r cosine theta. And accordingly, and similarly, this length, okay, so this, okay, let's see, this yellow part, this is the projection of this vector from the origin onto the xy plane, and the length of this projected vector should be r, so length of this vector should be r sine theta, because this is, so if we look at from, let's see, this angle, we have y, so actually this is xy plane, and this is z, and this is theta, and this is cosine, r cosine theta, so this is r sine theta, this length is r, right? So then we project this yellow line onto x-axis or y-axis, okay? But we have this angle phi here, so we project this this vector onto x-axis, so this length should be r sine theta cosine phi, and this length should be r sine theta sine phi. So the transform of these values x, y, z should be given by this. Sine phi. And r varies from 0 to infinity. Actually, it should be open. And phi, theta, should vary from 0 to, phi varies from 0 to pi. And phi varies between 0 and 2 pi. Or depending on the application, phi may vary from negative pi to pi. And from this set of equations, we can calculate the Jacobian. So that is x, partial derivative of x with respect to r, and with respect to theta, with respect to phi. And the partial derivatives of y with respect to r, theta, and phi. And the partial derivatives of z with respect to r, with respect to theta, with respect to phi. So if you try to calculate this, after all, you should try that. And after all, we have r squared sine theta. Okay. In the case of two-dimensional polar coordinate, the Jacobian was just r. But in the three-dimensional spherical coordinates, it's r squared sine theta. Now let's go back to the example of calculating the volume of a sphere. So the volume of the sphere is given by this. And of course, this region B is this, is the sphere. Okay, so okay, wait a minute. So R is of course defined by the square root of x squared plus y squared plus z squared. Okay. In this case, this can be calculated as this. So R varies from 0 to a, and theta varies from 0 to pi, and phi varies from 0 to 2 pi. Okay, and that's but we have Jacobian here, so that should be r squared sine theta d theta. Oh, wait a minute, sine theta d phi actually. Okay, so first let's calculate this part. Since there are no phi's inside, so it's just 2 pi. So the result is r squared sine theta times 2 pi. Maybe I should put the theta here instead of here. Anyway, then we integrate with respect to theta. So that would be, so let's put r squared and 2 pi outside. So 2 pi and r squared here, and the result of integration, so that would be cosine theta from 0 to pi in dr. So that is a negative 1, negative 1 and 0 minus 1, so that would be 2 r squared and dr. So that will be 4 pi and r cubed over 3, 0 a, and that is 4 pi a cubed over 3. So that is the volume of the sphere as we know it. Now let's consider a little bit more complicated problem. Suppose we have two cylinders and both cylinders have the same radius. Let's say A. So one cylinder, and there's another cylinder with the same radius but different length. Okay, so the radius of this one is R. Not R, it's A. And also for this, the radius is A. And and we intersect these two cylinders at the middle points. Okay, so it will look like this. And let's see, the length, the height of this cylinder is W. The height of this cylinder is H. Then let's call this cylinder C1 and this cylinder C2, and the combined solid is the union of C1 and C2. So what is the volume of this solid C? So the question is this. Okay, so to solve this problem, we put the axis of this cylinder onto the x-axis, and we put this the second cylinder along the z-axis. Z-axis. So let's see. And C1 can be defined as the point in space. So it's along the x-axis, and this is the middle point, so that's the origin. So this point on the x-axis would be h half, and this point on the x-axis will be negative h half. So that's x. And for y and z, so there should be y-axis somewhere here. So for y and z, we have a circle. So if we cut this cylinder at any plane perpendicular to the x-axis, we have a circle. So that will be y squared plus z squared less than or equal to a squared, because the radius is a. And C2. Similarly, we can define that as, so it's parallel to the z-axis. So that would be the height will be negative double half is the lower bound of the z coordinate, and on the xy plane we have a circle. So x squared plus y squared is less than or equal to a squared. And now, in order to calculate the volume of this, that will be the volume of C1 plus volume of C2 minus the volume of the intersection of C1 and C2. So we want to find this intersection. And that would be, so this and this. So let's see, we should have x squared plus y squared less than or equal to a squared, and y squared plus z squared less than or equal to a squared. Okay. Actually, we're implicitly assuming that w half is greater than a, and h half is greater than a. Okay. So the volume of C1 is pi a squared times h, and the volume of C2 is pi a squared times w. And for the volume of this intersection, it's a little bit complicated. So that is, let's call this region. Let's see. Actually, using the symmetry, we don't have to integrate for all these region, but it's symmetric around the origin and x-axis. No, it's symmetric around, yeah, x-axis and z-axis. So we can just, instead of this itself, we can define the region on the first so all x, y, z can be all positive, and x is non-negative, y is non-negative, z is non-negative. So if we calculate the volume of this and multiply that by 8, then we have the volume of this intersection of C1 and C2. So that is, we calculate the volume of this part. Wait a minute. X is, so maybe this part. It's hard to visualize, but so this part is above the xy plane and before the zx plane. Okay, so that specifies this condition. So the volume of C1 intersection C2 is 8 times the volume of W. Okay, so what is this volume then? To do that, let's define the two-dimensional region xy such that x squared plus y squared is less than a squared. So that corresponds to this, and x non-negative and y non-negative. Okay, so then we can calculate the volume of this as this. So first we calculate the double integral, and for the value of z, let's see, this one, z is less than or equal to a squared minus y squared, and z is positive or non-negative, so from 0 to square root of a squared minus y squared, and that is, if you integrate this, we have square root of a squared minus y squared dx dy. Then let's integrate this from with respect to x first. So dy dx, and in this case, let's see. So what's the range of x here? So y should move from 0 to a, and in that case x should move from using this. So that will be x squared is less than or equal to a squared minus y squared. So x should move from 0 to square root of a squared minus y squared. But there is no x here in the function, so it's just this quantity times x from 0 to this square root of a squared minus y squared dy, and that is a squared minus y squared dy, and that is, let's see, a squared y minus y cubed over 3 from 0 to a. That is a cubed minus a cubed over 3. That is 2a cubed over 3. So if we multiply this quantity by 8, we have the volume of the intersection. So 8 times 16a cubed over 3. So after all, the volume we wanted to calculate was a squared pi and h plus w minus this. So that's it. Next, consider solids of revolution. Sometimes we want to calculate the volume of a solid made by rotating a curve. So let's explain this. Suppose we have x and y here. Suppose we have this curve. So let's say y is equal to f of x. So this is just a two-dimensional plane, but consider the third dimension and rotate this curve around the x-axis. So something like this. So this rotation defines a solid, which is a solid of called a solid of revolution. More formally, such a solid of revolution can be defined in this way: x, y, z. So it's a set of points, and let's say this this is x varies from a to b, and y squared plus z squared is less than or equal to f of x squared, right? So so this height is f of x. So if we rotate this, we keep this distance from the x-axis constant. So that will be described by this equation of a circle, or or equation of a disk, inequality of a disk. Okay, so the distance from the x-axis is less than the value of f of x. Okay, and in this case, x-axis is called the axis of revolution. Of course, we can define a solid of revolution by rotating around the y-axis or z-axis if we have an appropriate function to define those. Now let us show that the volume of this solid of revolution is given by the following equation. AB and f of x squared and dx. Okay, to show this, let us define this set d of x that is on the yz plane, defined as let's see, y squared plus z squared less than or equal to f of x squared. Okay, so the volume of this solid of revolution is given by this. V and dx, dy, dz, which is equal to x varies from a to b, and y and z varies over this region d of x. Now here we use the polar coordinates of y and z. So if we use this, then this volume becomes a b dx, and so this radius varies from 0 to f of x, assuming f of x is positive. And the Jacobian is r, so dr, and the angle theta varies from 0 to 2 pi. So that becomes 2r squared and 0 to f of x times 2 pi. So, and dr. So that is, so 2 will be cancelled, and pi comes out, and ab and f of x squared dx, actually, dx. So that's it.